Chapter 23, Aldehydes and Ketones. Aldehydes and ketones both have a carbonyl group. So we have this double bond between a carbon and an oxygen. Aldehydes are terminal, meaning they have a hydrogen at the end. You can only find an aldehyde at the very end of the molecule. Whereas ketones have carbon groups on both sides. They're secondary, and so they're found in the middle of groups. You can have alkyl groups on both sides, a mix of an alkyl and an aryl, like a benzene group, or two benzene groups. The aldehyde group is often written as capital C, capital H, capital O, which is equivalent to this aldehyde group. The ketone group is often written as CO, signifying the carbonyl group in the middle of the molecule. The IUPAC rules for naming aldehydes. We first find the longest continuous chain of carbon that contains the aldehyde group. The aldehyde carbon is always carbon number 1. Then we drop an E from the corresponding alkane parent name and add Al. So hexane becomes hexanal. Ethane becomes ethanal. Propane becomes propanal. So you lose the E from the parent alkane and you get an Al at the end. Notice that the aldehyde carbon is not given a number in the name because it has to be at carbon number 1. Aldehydes are always at the ends of a molecule, and that's where you start counting at. Ethane is the longest chain that contains 2 carbons here, so this ethane becomes ethanal. Here we have 4-methylhexanol. So 4-methylhexanal. And the pronunciation is difficult because alcohols end in an OL, which is an ul, and aldehydes end in an AL, which is an al. But ul and al sound similar, so you have to listen carefully on the difference between those two. The simplest aromatic aldehyde is benzaldehyde. So this is a molecule of benzaldehyde. It's very fragrant. It smells like a bitter almond oil, or it has like a cherry fragrance to it, but for cooking they call it bitter almond. And it oxidizes very easily to benzoic acid. So if you have a bottle of benzaldehyde, you'll notice a white crystalline solid that collects around the outer lip of the bottle because that's where it's being oxidized to benzoic acid. Dialdehydes, both ends of the molecule have an aldehyde group, and so we get dial, butane dial. Just like with 2 alcohols, it was a diol. With 2 aldehydes, it's a dial. So butane dial. Give a name for the following compound. Again, your aldehyde group has to be carbon 1. So 1, 2, there's a methyl group on 3, then 4, 5. So we have 3-methylpentanal. 3-methylpentanal. Again, our longest carbon chain was 5. 1, 2, 3, 4, 5. The carbon with the aldehyde is carbon 1, and then we had a methyl group coming off of carbon 3. Write the structure of phenylethanal. Well, here we have the phenyl group coming off of our ethanal. IUPAC names for naming ketones. Name the longest continuous carbon chain that contains the C double bond O group. Drop the E from the corresponding alkane name and add -one. Propane becomes propanone. Butane becomes butanone. Pentane becomes pentanone. You can't have a ketone with just 1 or 2 carbons because if you only have 1 or 2 carbons, it's going to be at a terminal carbon. So when you have the carbonyl group on just a carbon, you get formaldehyde. And that's an aldehyde. Thus formaldehyde. With two carbons, they're both terminal carbons, and so regardless of which one you put the double bond on, it's also going to have an H there. It's going to have to be an aldehyde. So with 1 and 2 carbons, you only get aldehydes. To get an actual ketone, we need at least 3 carbons. And so acetone, or propanone, is the smallest ketone we're going to find here. An alternative non-IUPAC method. We list the names of the alkyl or aromatic groups attached to the carbonyl carbon followed by the word ketone. So you name, kind of like with the common name for ethers. Here we have methyl ethyl ketone, whereas before we had things like methyl ethyl ether. You were naming the 2 alkyl groups on both sides of your functional group. Here we're doing the same thing, except methyl ethyl ketone. And so the official name here is 1-phenyl ethanone, because the phenyl group is coming off of the 1 carbon. Or the common name, methyl phenyl ketone. Over here, ethyl phenyl ketone, or 1-phenyl 1-propanone. Write the structure of butyl ethyl ketone. We have butyl. Whoops. Butyl. Ethyl. And then ketone. Butyl ethyl ketone. Give the IUPAC names for the following compounds. Well, here, 2-methyl 6-bromo 4-octanone. So again, you want the smallest number on the ketone. That's the highest priority group. So if we start counting from this side, it's 1, 2, 3. It's on the 4 carbon. Let's check the other side. 1, 2, 3, 4. It'd be 5. And so we start counting on this carbon, because that puts it on the 4th, whereas if we started from the other side, that would be on the 5th, and 4 is a smaller number. So it's a 4-octanone, and on off of carbon 2 we have a methyl group, and off of carbon 6 we have a bromo. And if we look at this one, here we have an aldehyde, so we know this has to be carbon 1. Then off of carbon 2 and 4 we have chlorine groups, 2,4-dichloropentanal. So you had 5 carbons with the aldehyde group, so it was a pentanal. Then off of carbons 2 and 4 we have chlorine groups, so 2 chloros dichloro, 2,4-dichloropentanal. Cyclohexanone. Give a cyclohexane ring with the ketone group. Bonding and physical properties. The carbonyl carbon is sp2 hybridized. So that second bond is a pi bond. Just like we saw with the alkenes, when there's a double bond, one of them is a sigma bond, but one of them is a pi bond. And the oxygen is a lot more electronegative than the carbon, and so it draws electron density towards the oxygen, making this carbon pretty positive, which actually makes it pretty chemically reactive. So negative charge will attack that carbon, giving ketones a lot of chemistry. So because of this electronegativity difference, this carbon is partially charged and will then be attacked by negative charge and really participate in a huge amount of chemistry. And again, that pi bond is super reactive, and so when things strike into this carbon, this pi bond comes up to the oxygen. It cannot hydrogen bond to itself because there is no hydrogen atom attached to the oxygen. So there is no protic hydrogen in the ketone. And therefore it has a lower boiling point than a corresponding alcohol of similar molar mass. So we see the difference between propanol, the alcohol, and then the aldehyde and ketone. Much lower boiling points because you don't have any hydrogen bonding. Low molar mass aldehydes and ketones are soluble in water, like acetone is completely soluble in water. The lower molar mass aldehydes have a penetrating, disagreeable odor. As the molar mass increases, the odor becomes a lot more fragrant and people start liking it a lot more. So benzaldehyde is pretty aromatic. It smells like cherries. It's called the oil of bitter almonds. Cinnamaldehyde is what gives cinnamon its fragrance. Carvone, this is what gives spearmint its spearmintiness. And notice the ketone there, super important. Muscone, this is the gland of the male musk deer. It's used in perfume for muskiness. Civitone, this is a secretion of the civet cat. And this is used in a lot of perfumes as a fixer. Other naturally occurring aldehydes and ketones. Glucose is sugar, ribose. This is a sugar you make RNA out of. And you can deoxygenate it to make deoxyribose for DNA. Fructose, another natural sugar found in fruits. And then a glucose and a fructose can combine to form sucrose, which is table sugar. Citral, which is found in the oil of lemon and gives its citrusness. And then here we see vitamin K1, which is a vitamin which stops bleeding. So it helps the body clot blood. So rank these molecules based on boiling point from lowest to highest. Well, we know the highest will be the alcohol because this has hydrogen bonding. They're all about the same mass. So the alcohol will be the highest boiling point. Heptane has no functional groups whatsoever. And so whereas the hexanone has a ketone group, you get a little bit of intermolecular forces. You get none in heptane. So it's already ranked. Well, I guess it's ranked opposite. So the lowest boiling point will be heptane. Second lowest boiling point, 3-hexanone. And the highest boiling point, 3-hexanol. And all that's changing is the degree of intermolecular forces. You have just van der Waals forces in heptane. Then in hexanone we have partial positives and partial negatives. The dipole in that carbonyl, that C double bond O, the O is partially negative and the C is partially positive. And those partial positives and negatives attract each other, giving you more intermolecular forces. And then finally with hexanol we have full out hydrogen bonding, which is one of the strongest intermolecular forces. The carbonyl functional group is the reactive site for aldehydes and ketones. These compounds undergo three broad classes of reactions. You can oxidize aldehydes to carboxylic acids. You don't oxidize ketones because that would require breaking a carbon-carbon bond, which is very difficult. We can reduce both. We can reduce both aldehydes and ketones down to alcohols. And they can both do addition reactions. So with oxidation, here we can use chromic acid or chromates to oxidize an aldehyde to the carboxylic acid. That's a relatively easy reaction to pull off. This is one of the tests, the Tollin tests, to test for the presence of an aldehyde. If an aldehyde is present, it will reduce silver from silver plus to metallic silver, and then this will coat the glass beaker with a mirror finish. So you'll see a deposition of silver on a glass surface, making it a mirror, and that is proof of the presence of aldehydes. And that they call it the silver mirror test because it makes your beaker into a silver mirror as the silver precipitates onto the glass.